You ever look at a computer chip and just wonder what's really happening inside? I mean, how do these abstract rules and little pulses of electricity turn into something real, something you can actually see and control, like an LED blinking on and off? Well, that's exactly the journey we're going on today. We're going to go from the fundamental design philosophies of a processor all the way to the practical magic of making an Arduino interact with the world around it.
Okay, so here's our roadmap for this explainer. First, we'll look at the two big philosophies for building processors. Then, we'll get into how computers actually do math. After that, we'll check out the computer on a chip that powers the Arduino, meet its pins, and finally, we'll put it all together to control something in the real world. Let's get started. All right, section 1. Two philosophies for processors. And really, it all comes down to the instructions. See, to really get what's going on, you have to realize that not all processors are built the same. They have these two competing design ideas at their core, and it's all about what kind of instructions they're built to understand. So that really begs the question, right? If the whole point of a processor is just to, well, process things, why aren't they all designed the same way? The answer comes down to this really fundamental choice. Do you bake all the complexity right into the hardware? Or do you keep the hardware simple and let the software do the heavy lifting? And that right there is the huge difference between CISC and RISC. And this table, it just lays it all out perfectly. On one side, you've got CISC, that's Complex Instruction Set Computer. It crams a huge library of really specific instructions right into the hardware. Think about the Intel chips you find in a lot of PCs. But on the other side, you've got RISC, Reduced Instruction Set Computer. This approach makes the hardware way simpler with just a core set of basic instructions, and it makes the software do more of the work. That's the idea behind the super efficient ARM chips in, your phone, and as we're about to see, in our Arduino. So let's zoom in on CISC for a second. The best way to think about it is like having this gigantic toolbox with every single specialized tool you could ever dream of. The upside, you can do a really complicated job with just one single powerful instruction. But the downside is huge. The hardware gets super complex, and what's crazy is that most of the time, a program only ends up using maybe 20% of those special tools. The rest just sit there. Now RISC, it's the total opposite. Instead of that massive toolbox, it's more like a small, curated set of super simple but incredibly fast and efficient tools. Because every instruction is so basic, most of them can be done in a single tick of the processor's clock. That makes it lightning fast. So what's the catch? Well, you need to string together more of those simple instructions to do the same job, and you need really fast memory to keep shoveling them into the processor. Okay, moving on to section 2, how computers do math. Specifically, the elegance of binary multiplication. So we've got these processors that can run instructions. Great, but how do they actually, compute? How do they do math? And it gets really tricky when you throw negative numbers into the mix. Turns out, there's a really brilliant and clever algorithm that solves this whole problem. And that secret sauce is called Booth's algorithm. It is just a ridiculously clever way for a computer to multiply binary numbers and not get tripped up by whether they're positive or negative. It's designed to work with numbers that are already in a special format for signed numbers, which means it doesn't have to stop and do a bunch of messy conversions in the middle of a calculation. It just works. And you can see just how simple and elegant it is right here. At its heart, it's really just a loop. The computer just looks at the last two bits of the number. Based on what it sees, a 1 and a 0 or a 0 and a 1, it decides to either add, subtract, or just do nothing. Then it shifts everything one spot or the right, and then it just does it again and again. It's this simple cycle. Examine, act, shift, over and over, until you've got your answer. Okay, next up. A computer on a chip. We're going from those abstract rules to physical silicon. We've talked about the big ideas, the philosophies of processor design, and the logic of how computers do math. Now, let's see how all that theory gets squeezed into a tiny physical chip that you can literally hold in your hand. And here it is. This is the ATmega 328P. This little guy is the brain of the super popular Arduino Uno board. So which architecture do you think it uses? Yep, you guessed it. It's based on AVR RISC. That whole idea of a simple, fast, and efficient toolkit we were just talking about, it's right at the heart of this very chip. And this thing isn't just a processor, it's a whole computer packed onto one chip. It's got that RISC CPU core, sure, but it also has everything else it needs to run all by itself. It has flash memory, which is where your code gets stored. It's got SRAM, which is like its short-term memory for variables while it's running. It even has EEPROM for data you need to remember even when the power's off. Plus, it has all these built-in tools, called peripherals, that help it talk to the outside world. So, on to our next section. Meet the Arduino pins. This is your connection to the physical world. I mean, we've got this awesome little computer on a chip, right? But how do we actually get signals in and out of it? Well, that's what the Arduino board is for. It's basically just a convenient adapter that takes all the powerful capabilities of that 18MEGA328P chip and breaks them out into these easy-to-use pins. And these pins really come in two main flavors. You've got your digital pins, which are super simple. Think of them like a light switch. They are either all the way on, which we call a high state, or they're all the way off, a low state. That's it. Perfect for things like checking if a button is pressed or just turning an LED on. Then you have the analog pins. These are more like a dimmer knob. They can read a whole range of values in between on and off, which is absolutely crucial when you're working with sensors that give you changing variable readings. But what if you want that dimmer knob control, but all you have is a digital pin, a simple on-off switch? Well, there's an incredibly clever trick for that. It's a technique called pulse width modulation, or PWM, and it's basically a way to fake an analog signal using a pin that can only be on or off. So here's the magic behind it. Instead of just staying on or staying off, the digital pin starts switching between on and off super fast. By changing the percentage of time it spends in the on state, which is something called the duty cycle, we can actually control the average voltage that comes out. So if you have a 5-volt pin and you set it to a 50% duty cycle, it's on half the time and off half the time. To a device like an LED, that looks like an average of 2.5 volts, and that's exactly how you can dim a lit or control the speed of a motor. All right, final section, controlling the real world. This is where we put the theory into practice with a sensor. We've gone all the way from processor theory to the actual chip to the pins that let us talk to it. Now let's tie it all together and actually use the Arduino to read some real data from the environment. So what you're looking at here is a really common LM35 temperature sensor, and we've got it hooked up to our Arduino. It's a tiny little thing with a very simple job. It outputs an analog voltage, and that voltage changes based on the temperature around it. The rule is simple. For every degree Celsius the temperature goes up, the sensor's output voltage goes up by 10 millivolts. And this whole process, this is the perfect summary of everything we've talked about. It's beautiful. Think about it. A physical property, temperature, gets turned into a changing analog voltage by the sensor. The Arduino's analog pin reads that voltage. Then, a special part inside the chip called an analog-to-digital converter, or ADC, takes that smooth, continuous signal and chops it up into a digital number, a number that its RISC processor can finally understand and work with. The Arduino reads the voltage. It maps an input voltage between 0V and 5V to an integer value between 0 and 1023. And that right there, that really gets to the heart of it. That single act of mapping, of translating a real-world voltage into a number, that is the fundamental bridge. It's the exact point where the messy analog world we live in gets translated into the clean digital language that the computer speaks. So this leaves us with a really big question. If one tiny, super low-cost chip can do all of this, if it can sense its own environment, what happens when you connect millions or even billions of them to the internet? Because this simple little setup, this is the fundamental building block for almost every smart device you can think of. Your smart thermostat, sensors in a factory, you name it. If you really understand how this one chip senses the world around it, you get the core principle behind the entire Internet of Things. And that's a pretty powerful idea.